get started. So when we last left off, we discussed extensively this concept of electrophilic substitution reactions of alkenes, such as hydrobromination, such as alkene bromination and chlorination. So in this case, let's take a look at the following two mechanisms, and let's look at these two electrophilic substitution reactions, and let's try to draw a reasonable mechanism for each. Let's start off with this first example that we'll label A. Let's try to utilize the annotate tool or our pen and paper, and let's try to draw an arrow pushing mechanism and the major product for this following reaction. Remembering our rule for this type of electrophilic substitution reaction, that generally this substitution reaction follows Markovnikov's rule, where we observe attack of our halogen on the most substituted carbon in our alkene. In other words, the carbon that can most readily stabilize and accommodate a carbocation. So, would someone care to volunteer to draw an arrow pushing mechanism for this first reaction, or draw the proposed product from this first reaction? So let's take 2 to 3 minutes at the start of this period, and let's sort of get back in the rhythm of drawing mechanisms and dealing with these electrophilic substitution reactions. So don't be shy to use the annotate tool or your pen and paper to draw the mechanism and predict the major product for this reaction. Rather than just focusing on memorizing the product patterns, I want you really to think about these reactions from a mechanistic perspective. If you draw the mechanism will lead you to the product. So, would anyone like to break out the annotate tool and draw out a mechanism for this first reaction? And in turn, tell us what product will generate as the major product. You can also share a photo in the chat of your predicted major product and the mechanism, or you could just share a drawing of the major product, and then another student or your instructor, myself, can fill in the mechanism. So, given the following reaction, what would you expect would be the major product? Okay, so we have protonation of our alkene and generation of the bromide anion. So what do we make after that first step? We're getting somewhere now. What do we make after that first step? What's our intermediate? Okay, so we have a carbocation, and interestingly enough, this carbocation was drawn in a very specific way. Would someone care to tell me, why do we make a tertiary carbocation? What is the motivation? Why do we make a tertiary carbocation over a primary? Stability. Okay, perfect. Almost an immediate response in the chat. Exactly right. The tertiary carbocation's more stable. There's a greater amount of stabilization via hyperconjugation because we have more substituents, more adjacent sigma bonds present on our adjacent carbons to our carbocation. Okay, wonderful, wonderful. So then, after we make this carbocation, what is the next step? And this is the payoff. This is the second step in this substitution reaction. And in turn, it will tell us in turn the location of our bromide in the final product and the structure of our final product. Would someone like to draw the final step for this reaction? So once we make our carbocation, we have bromide anion floating around. And what happens with that bromide anion? So we see a student response where we have the bromide adding at our tertiary carbocation site to form a carbon-bromine bond. Would someone like to draw an arrow pushing mechanism for that step? Would someone like to draw out an arrow pushing mechanism to help us see that attack step to form our critical carbon-bromine bond? Overall, what does the class think of this predicted product? Do you agree with this product prediction? Do you disagree? What's the class opinion on this so far? And I'd really like to see as many responses from the class as possible just to get a sense of what everyone's thinking and how you're working through and reasoning through these mechanisms. Okay, so in this case, we see a fair amount of agreement here. So let's talk about step by step how we reach that product. Well, the first step is we protonate our alkene, and in turn, we generate our tertiary carbocation. From there, our bromide anion will attack this highly reactive carbocation. In this case, our carbocation is at the tertiary position, so we see attack at the tertiary position following Markovnikov's rule. And that in turn gives us the following product. Does this make sense to everyone so far? Does this make sense to everyone so far?
Yeah.
Perfect, perfect. So let's take a look at this next reaction, and this one's a little bit different. It involves a combination of our typical electrophilic substitution mechanism with a hydride shift mechanism. Would anyone like to propose a step-by-step mechanism for the following reaction? And it takes at least 3 unique steps to go from this reactant to the product shown in this note page. So let's break out our annotate tool or our pen and paper. Don't be shy to share your responses on the class whiteboard using the annotate tool, or you can share your responses as a picture in the chat, and I'd be happy to take a look at it and transcribe it onto the class whiteboard. So let's get started working on this example. And I'd like to see students sharing their responses on the class whiteboard using the annotate tool. So don't be shy to volunteer your proposed mechanism for this reaction, or even to contribute an initial step in this reaction. Even just a starting step is enough to get things started and to help spark further contributions from the class. So would anyone like to start us off on this mechanism? You don't necessarily even have to draw all the steps, just enough to get us started. Would anyone like to contribute a first step for this reaction? So we're working under typical electrophilic substitution conditions. So what would our first step be? What was the first step that we drew in the previous mechanism? What was the first step? You can type it in the chat or you can draw it using the annotate tool. I really want to see that students are comfortable drawing mechanisms out. So we have in the chat, I see proton abstraction. Okay. So I have a question for you then. So am I going to protonate at the position in purple, or am I going to protonate at the position in red? And why? Which position will get protonated? Which position is protonated preferentially, purple or red? Think really carefully about this. So we have one vote for red. Does anyone have another perspective? Does anyone agree with that? Where are we gonna observe protonation? Which site, which arrow is best reflective for this mechanism? The arrow in red or the arrow in purple? And I'd like to see the class contributing. You can even draw it out if you want using the annotate tool. I would encourage you to practice the act of drawing the arrows for this mechanism, as that is the skill that you'll be using time and time again. So we have one vote for the reaction arrow in red. What about any other comments? Does everyone agree with that? Does everyone disagree with that? What do we think? How should we draw the first step's reaction arrow? How should we draw the first step in an arrow pushing mechanism for protonation? So our current class discussion, we're proposing if we protonate following the mechanism in red. So let's entertain that possibility. So if we protonate following the mechanism in red, so let's draw this arrow formally then. We would get the following product. So my question to you is this the most stable carbocation that we can generate? Is this the kinetically preferred carbocation intermediate? Is this the kinetically preferred carbocation intermediate? Are we good to continue on with this mechanism? Does this look reasonable to everyone? And just to help shape everyone's perspective and help everyone draw a conclusion for this, if we drew the mechanism out in purple, we would get the following carbocation intermediate. Now, once we've drawn out the carbocation intermediates, and we have this new data point that we should always be considering, what does everyone think? Which carbocation intermediate is preferred? Which carbocation intermediate is preferentially generated? Which carbocation intermediate is the kinetic intermediate? And we see overwhelmingly in the chat, suddenly everyone's talking and noting that the purple carbocation intermediate is preferred. That's exactly right. So in order to get this purple carbocation intermediate, where do we protonate? So our proton must end up at this bottom carbon. So then drawing our arrow, we protonate our alkene, and in turn we generate the following carbocation. Does that make sense to everyone so far? Does everyone understand this first step? You protonate your alkene and generate the most stable carbocation. That's the kinetically preferred carbocation for this electrophilic substitution reaction. Okay, now I need you to take off from here in this relay race. There are still 2 more steps to go. What's our next step? If we want our chloride on this other tertiary position, how do we move our carbocation around? And I'll give you a hint, and I'll draw out this proton here. And we already see students typing in the chat, hydride shift. Would someone like to draw the reaction arrow for that hydride shift? How do we draw that hydride shift to generate our desired carbocation? Would someone like to draw that using the annotate tool? You can also send a picture in the chat. Both would work. Okay, so we have our arrow drawn from the carbon-hydrogen bond to our carbocation. Yep, that looks perfectly reasonable. Just to clean up the notation a little bit, you want to make sure your arrow starts at the desired bond and ends at the desired electrophilic atom that you're forming your new bond at. That in turn gives us the following product. Now, this hydride shift it's not as fast as other hydride shifts because you're trading one carbocation for another carbocation. Both of these carbocations are clearly tertiary, though there's some benefit to getting the carbocation out of the ring system as you're mitigating a little bit of strain. Now looking at this system, how do we finish off this mechanism and get to our final product? How do we finish off this mechanism and get to our final product? What's our last step that we need to form this carbon-chlorine bond? What's our last step that we covered last session? What's our last step in this reaction? Perfect, perfect. So we have drawn the attack of our chloride on our carbocation. Exactly right. So we draw an arrow from the lone pair on chloride to the carbocation carbon. That forms our desired carbon-chlorine bond, and that completes this mechanism. So the only thing that's new, only thing that we've added from our previous class session is the presence of this hydride shift. For those who are curious to rationalize why this hydride shift may occur, when you have a planar carbon, you've locked your substituents around that carbon into 120-degree bond angles, and that introduces a little bit of strain. So moving the carbocation outside of the ring could introduce a little bit of steric benefits, though this hydride shift doesn't occur very readily. Any other questions on this example where we've drawn two mechanisms incorporating electrophilic substitution and hydride shifts? Any questions? Okay, if not, let's keep going and let's talk a little bit about stereochemistry. Now, this is a big deal. We ideally as chemists want to generate products with defined stereochemistry because the stereochemistry drastically impacts the properties, and if possible, we'd want to get some enantiomer selectivity because we know from our previous discussion of enantiomers that different enantiomers can have different biological activities. Okay, so if we think a little bit about the mechanism for electrophilic alkene addition, we protonate our alkene and we generate a trigonal planar carbocation. Note the word planar, flat. So there are two possible faces for attack. We can either attack our carbocation from the top or the bottom, and there's no clear preference for this planar species, and there's no facial selectivity inherently from our reactant molecule. So in turn, we get a 50-50 mixture of each of the enantiomers. So we end up with a racemate. In this case, we deal with a 50-50 mixture of enantiomers. If there are other stereocenters, we'd end up with a mixture of diastereomers. Does everyone see how because we have a flat intermediate, a planar intermediate, and we have two different potential faces to attack from, we end up with two unique products generated with roughly equal preference? Does everyone see why we get a mixture of enantiomers in this case? Does that make sense to everyone? Can I get some feedback in the chat? Does everyone see how in a normal common substrate for electrophilic substitution, you're going to get a mixture of enantiomers? Does that make sense to everyone? And that's because it stems from our attack on two different possible faces of our molecule. Any questions on that idea? Well, we can build on that because if you have appropriate steric hindrance on one face of your molecule, you can actually bias the stereochemistry for this alkene addition. So for example, in this case, we have this really bulky T-butyl group blocking the top face. So we've essentially blocked our top face. And in turn, what that means is after our first protonation step, we in turn generate a carbocation intermediate. And now what's really cool about this step, let me draw the carbocation on the correct carbon. They're identical, but, well, or functionally degenerate, but let's draw so that it matches our indicated product. Now, because this T-butyl group blocks the top face, when our bromine tries to attack from the top face, when our bromide anion tries to attack from the top face, it is blocked by this bulky T-butyl group. So in turn, what that means is that we end up, because our reactant molecule has a certain shape that is biased, that blocks one of the possible faces that you can attack from, you end up with selectivity for one of your desired product stereoisomers. This is reactant-based or substrate-based selectivity. Does everyone get how this works? Does everyone see how the shape of your molecule directly impacts the stereochemical outcome of your reaction? Does everyone see why this bromide, why the bromine ends up incorporated on the opposite face relative to this giant T-butyl group on top? So when you think about facial selectivity for molecules with no steric bias, you often get a mixture of attacks from the top and bottom face from your planar carbocation intermediate. But in this case, because the top face of the molecule is substantially hindered by this bulky T-butyl group, you end up with preferential attack from the bottom face. This is known as substrate controlled selectivity. In other words, substrate control. Oops, one moment. This is an important concept that will be discussed in both later in this course and in upper division organic courses. So keep in mind that the shape of the substrate can impact the stereochemical outcome of your reaction. Okay. So continuing on, let's talk a little bit about how we make alkenes. And this will be a preview for our next chapter on elimination reactions. So alkenes are commonly made from the elimination of a alkyl halide. So typically, as elimination is favored at higher temperatures, we use heat and a strong base, such as potassium hydroxide. So for example, if you treat the following alkyl bromide with potassium hydroxide and you heat it to a high enough temperature, you'll generate the desired alkene. So in terms of mechanistically what's going on here, the hydroxide is grabbing a proton and we are simultaneously generating our alkene and eliminating our bromide ion. So this is a concerted process, and this would be known as a quote-unquote E2 reaction. More on that in later chapters. We're now just talking about how do we make these alkenes that we're going to functionalize and derivatize using a variety of different reactions. Okay, so that's one method to make alkenes. The other method is elimination of water from an alcohol via dehydration. This typically occurs with strong acid and heat. So we typically use concentrated sulfuric acid and you heat this alcohol to really high temperatures. Have we seen this reaction before? Have we seen this reaction anywhere? Does this reaction ring a bell for anyone? Did we watch a video of this reaction previously in lab? Did we do something in lab related to this? What lab have we run this reaction before? I'll start drawing and let's see if anyone picks up on it. Did we run a reaction very similar to this dehydration? Have we run a dehydration? Yep, the lab we're doing now. Yep. So in that case, we took our 2-butanol and heated it in the presence of concentrated sulfuric acid. And in turn, we generated a mixture of elimination products. So let's talk a little bit about the mechanism behind this reaction. Let's talk a little bit about the mechanism behind this reaction. And it's a multi-step mechanism, and it's important that you get familiar with this common pattern that we often see. So the first step in this mechanism is protonation, which I like to call the activation step. We are making this alcohol a more effective leaving group. So in this case, we protonate our alcohol and we generate the following protonated species. Now that we've generated the following protonated species, the alcohol then leaves and we generate a carbocation. Once our carbocation is generated, all we have to do now is water just pulls off a proton and we eliminate and we regenerate and form our alkene. This is known as a stereotypical E1 elimination. And the hallmark of an E1 elimination is the carbocation intermediate. Remember how we talked about the arrow pushing mechanism for the E1 reaction in our mechanisms chapter? Does this process make sense to everyone? Does everyone see how we can make alkenes from alcohols using strong acids? Does everyone get that part? That we can make an alkene from an alcohol using strong acid? And does everyone see why the strong acid is important? It protonates the alcohol, activates it, and in turn makes it more likely to leave. Does this process make sense to everyone? Does everyone understand the common methods that we can make alkenes? Can I get some confirmation in the chat for that? Okay, so once we have our alkenes, we can now start to talk a little bit about how to derivatize these alkenes. Now, one way that we can derivatize these alkenes is through electrophilic substitution reactions using other acidic species. So in this case, we're treating this alkene with H+ and water. So I'd like you to think of this like H3O+, similar to how you dealt with HCl. So if we're following our general scheme for electrophilic substitution, what is our first step going to be if we have H3O+ floating around? What is our first step going to be if we have a strong acid floating around? What's our first step going to be? Keep in mind that this is a reversible reaction. What's the first step that we typically see in electrophilic substitution? What's the first step that we've seen time and time again for electrophilic substitution? Would anyone like to propose the first step in the chat? This is another type of electrophilic substitution reaction. And at the end of this process, we're going to potentially generate an alcohol. That's my first hint. So what's the first step in general for electrophilic substitution reactions? What's the first step that we've seen time and time again? You can also try and draw the first step using the annotate tool on the class whiteboard, but I'd like to see some class input to help drive this discussion forward. If we're dealing with electrophilic substitution, what's the first step? And to help everyone sort of get a sense of what's going on here, if I treated this with hydrochloric acid, what's the first thing that would happen? What's the first thing that we said if we treated something like this with hydrochloric acid? What's the first thing that we'd see for a typical electrophilic substitution reaction? What's the first thing that we'd see? Would anyone like to propose the start for this mechanism in the chat? So to provide you a hint, if we're dealing with electrophilic substitution under acidic conditions, the first step is protonation of our alkene. Now, if we have a choice, which carbocation would we make? Tertiary or secondary? Which carbocation is preferred? Tertiary, right? So then we generate the tertiary carbocation. And now, rather than chloride, we have a ton of water floating around. So what are we going to have attack our carbocation? What are we going to have attack our carbocation? What's going to attack our carbocation? Rather than chloride, what nucleophile, what species that is relatively electron rich do we have available? The oxygen of water, exactly right. So water is going to attack our carbocation, and in turn, we're going to generate this alcohol adduct. And then just so that way we're dealing with a neutral final product, water is going to regenerate H3O plus by pulling off our proton. So that in turn gives us a tertiary alcohol. And because we went through a carbocation intermediate and we can either attack from the top or the bottom face, we get a mixture of enantiomers. Does this idea make sense to everyone? The only thing that we have changed is that rather than chloride acting as our nucleophile, we have water. So the elimination of alcohols is a reversible process, and it depends on the concentration of acid and the temperature utilized. If you keep these reactions cold, you often have a very good chance of seeing this substitution. If you increase the temperature, you start to observe an increasing amount of elimination. Does this mechanism make sense to everyone? And does everyone understand why we get two different enantiomers? Why we get a mixture of enantiomers? Any questions on this example? Any questions on this example? Okay, so let's now try to apply what we've seen, and let's try to draw a mechanism for the following reaction. So we treat the following alkene with acid in the presence of a large amount of water. And I'd like us now to draw a mechanism, an arrow pushing mechanism for the following reaction. How do we go from reactants to products? So let's take about 3 to 4 minutes to work on this example. Don't be shy to share your responses using the annotate tool or by sharing a picture of your drawn mechanism in the chat. Or don't be shy to ask a question and I'd be happy to address it. So let's try and draw the mechanism for the following reaction, and we'll discuss this example in about 2 to 3 minutes. So we see a student typing in the chat that we're going to protonate our alkene. Would someone like to draw the mechanism for that first step using the annotate tool on our class whiteboard? How should we draw our alkene protonation? Okay. And then once we protonate, what type of carbocation will we make? What will our product look like? Perfect, perfect. So we have in the first step for this proposed mechanism, we protonate our alkene and we generate the more stable carbocation, which is our tertiary carbocation. Okay, now that we have our tertiary carbocation, what's our next step? So we have our tertiary carbocation and water floating around. So what would our next step be? What's the next step in this process? Yep, exactly right. We have the attack of water on our carbocation. Perfect, perfect. And that in turn generates a tertiary protonated alcohol. One, two, three, four, five. 1, 2, 3, 4, 5. Perfect. And now what's our last step? What's our last step? How do we get rid of that proton? What do we have sitting around that can pick up a proton? Perfect, perfect. We have deprotonation of our substrate using water. Exactly right, exactly right. So we have water, and water is going to come by and it's going to pick up a proton. Remember to break the proton-oxygen bond in your substrate, and that in turn generates our product and regenerates H3O+. So the acid is acting as a catalyst in this reaction. It's an acid catalyzed substitution reaction, or acid catalyzed hydration reaction more precisely. Great, it's great. So the class is getting a little more comfortable with these mechanisms, and they're more comfortable drawing steps for related reactions that all follow this general pattern for alkene substitution under electrophilic and acidic conditions. Does this make sense to everyone? Does this mechanism make sense to everyone? Okay, so let's keep going now. Let's keep going now. We're now going to add a small twist to this reaction, and I'd like you to draw or try to draw a mechanism for the following reaction. So this time we're treating our sample with an acid. Let's use hydrochloric acid just as an example. And this is going to trigger a very fast intramolecular reaction. So intra, within the same molecule. Now, it's still a acid catalyzed substitution reaction. So then what would the first step be? What would the first step be? Would someone like to try and draw the first step for this reaction using the annotate tool? What's the first step in an acid catalyzed hydration or acid catalyzed alkene substitution step? Protonation, yeah. And would someone like to draw out that protonation step using the arrow pushing tool? Would anyone like to try and draw that protonation step using the annotate tool? So we have the product drawn, but would you be able to draw the arrow pushing process that gets us to that product? If we have like hydrochloric acid, for example, could you draw out those? Perfect, perfect. Okay, so we're making some progress now. So let's summarize that progress. So we protonate our alkene, and as the class noted in the chat, we generate our tertiary carbocation. Okay, so now what's the next step? So we ideally want to form a carbon-oxygen bond. So how do we, what is attacking our carbocation? Is it water or is it the alcohol in our molecule? What does everyone think? Is water attacking our carbocation or is it the alcohol within our molecule? So we see some typing in the chat and they're saying the alcohol. Okay. So then how would we draw that? Would someone like to take a try to draw out in an arrow pushing method? How do we draw the attack of our alcohol on our carbocation? Yep, exactly right. So after the attack, of our carbocation by our alcohol, we're left with the following intermediate. We're left with the following protonated alcohol. And then in our last step, water just removes that proton to regenerate our neutral species. Does this process make sense to everyone? Does this process make sense? The only difference here, the only difference is that it's an intramolecular reaction rather than an intermolecular reaction. These reactions are very fast because you have your nucleophilic and electrophilic site. You have your two sites of reactivity placed very close together in space. So it allows for a very fast reaction. That's why this intramolecular reaction is often thousands to tens of thousands of times faster than the intermolecular variant. Okay, perfect, perfect. So let's talk about some other variations. How else can we substitute these relatively nucleophilic alkenes with different species? How can we form some more unique carbon, halogen, or carbon-carbon bonds from these alkenes? Well, we can add halogens to our alkenes, and it was found that bromine and chlorine add to alkenes to give 1,2-dihalides. This is a very important process, and it's also a stereospecific process, depending on your substrate. So one thing to keep in mind, you don't do this reaction with fluorine typically. It's very exothermic and will likely explode if you try to run it with most alkenes, because fluorine is so reactive and the carbon-fluorine bond formation is relatively exothermic. So you're typically not going to see alkene difluorination run with elemental fluorine. And for iodine, the product is unstable, so you typically don't observe a lot of the diiodide. That's not to say that you can't utilize iodine for variants of this reaction, but iodine is not particularly useful for dihalogenation. So when you think of chlorine and bromine, it's best thought of, when you think about chlorine and bromine, you can break it into a quote unquote Cl plus portion and a Cl minus portion, where one of our chlorine atoms is functioning as an electrophile, while the other chlorine atom is functioning as a nucleophile. Now, when we think a little bit about the stereochemistry, and this is really important, the stereochemistry of halogen addition to alkenes, the addition occurs in exclusively a trans arrangement, where we only observe the product that involves trans dibromination. We always observe the bromines on opposite faces of our molecule. Now that's really interesting when we observe this kind of stereospecificity, where we only observe the stereoisomers containing the trans arrangement of our bromine atoms. Now the obvious question then becomes, why are we observing this stereochemistry? And that really stems from the mechanism of bromine addition. So the first step in our mechanism is electrophilic addition of bromine in order to yield a bromonium ion. Now, of course, initially we can either observe attack from the top or bottom face. We can either observe attack from our top or the bottom face. There's no facial selectivity for this first bromonium ion formation step. Now, the bromonium ion is a pretty reactive electrophile, and the bromide ion is a good nucleophile. So in turn, bromide is going to attack from the opposite face at the most substituted carbon. Again, this brings to mind the idea of a carbocation-like intermediate. So in this case, we see stereospecificity, where we will always observe attack of bromide from the opposite face to our bromonium ion, giving us exclusively the trans addition product. Does everyone see how the bromonium ion and bromide are on opposite faces of our molecule? And does everyone see how this attack occurs from the opposite face to our bromonium ion? Perfect. So that partially explains why we observe the trans dibromination products rather than the cis dibromination products. So rather than memorize the stereochemistry of the products, focus more on the mechanism and understanding how the mechanism operates. Because you'll be seeing this general class of mechanism multiple times throughout this section. Okay, so let's try to predict the products of the following reaction, and we're going to work on these examples together. It's time for you to break out your model kits if you don't already have them out and ready to go, because we're going to utilize our model kits in order to predict the products from this reaction with the correct stereochemistry. So let's break out our model kit. Let's break out our model kit, and let's try to make a model for this first structure that we see here for this Z alkene. Now you may say, why are we making a model kit? Why are we making a model? Well, it's really important because it's going to help us visualize what is going on and the stereochemistry of our final products after we generate our bromonium ion and attack our bromonium ion. So let's put together a model of this reaction, and let's put together a model of this first reactant. Thankfully, the hydrogens are both on the same side, so the camera can't do anything too funny. Okay, so we're almost there. So let's put together a model of this first structure, and then we're going to talk a little bit about what's going to happen and what our bromonium ion is going to look like. Okay, so okay, can everyone see my screen here? Can everyone see my screen okay? Okay, so initially for our alkene, we have both of our carbon atoms on the same side of our alkene. Now, the bromonium ion can attack from either the top or the bottom face. It doesn't matter. There equivalent approaches for this flat molecule. So we're going to arbitrarily attack from the top face. And we're going to make the following bromonium ion. Does that make sense to everyone so far? Does everyone see how we attacked from the top face? So we made the following bromonium ion. Does that make sense to everyone? Okay, so we're just going to draw what we see. So in this first approach, so when we make our first bromonium ion, our alkene attacks and is attacked, and we kick out our electron density back to our other bromine atom. That in turn generates the following bromonium ion. And now what we're going to do is we're going to draw what we see. Okay? So I see both of these methyls. Are they pointing towards us or away from us? Are they pointing towards us or away from us? Towards us. So we're going to draw both the methyls with a wedge. We're going to draw the bromonium ion in the plane of the page, just flat. And are my hydrogens pointing towards us or away from us? Are the hydrogen, they're pointing away from us. Exactly right. Okay, so now what we're going to do, is we are going to attack this bromonium. Thankfully, both of our carbons are equally hindered. They have the same substitution, so we can attack at either of them. They're identical in terms of substitution. Let's arbitrarily attack at the left carbon. And we're going to attack from the opposite face to our bromonium ion. So we're going to attack. Okay, so we attack. So we form the bond and we break the bond. Does everyone see what our product looks like after the attack? Does everyone see what our product looks like after the attack? So just to summarize, we attacked our bromonium from the opposite face. We chose to attack at the left carbon because it's equally hindered to the right carbon. Does everyone see that attack? When we attack, we pop open our bromonium. Does everyone see that so far? Okay, so now we're going to draw what we see. And this, we have to be very careful of how we draw this. So I'm going to pretend this molecule is completely, I'm going to look at this bromine, carbon, carbon, and bromine, and I'm going to draw them perfectly flat. So we have our bromine, our two carbons, and our bromine. Now, where is this methyl pointing? Is this methyl pointing towards us or away from us? Towards us. So we're going to draw a wedge for our methyl group, and the hydrogen is still pointing away from us. Okay, what about this methyl group on the right? Is it pointing towards or away from us? Towards, right? And the hydrogen is pointing away from us. Perfect, perfect. Okay, now, one thing that we can do to make this easier to visualize is I'm going to rotate this molecule so now all of my carbons are flat. So if we do a little rotation and we set up our carbons in the typical zigzag pattern that we are so accustomed to. So if we set up our carbons in the typical zigzag pattern, so let's just draw what we see now after bond rotation. You can orient this molecule however you want. I just want to show you that this structure that we've drawn is equivalent to the following orientation. And now let's take a look. Now that we've set it up so our carbons are in the typical zigzag pattern that we commonly draw our straight chains in, my question to all of you is this hydrogen that we see on our leftmost carbon pointing towards us or away from us? How is this hydrogen pointing? Keeping in mind that the bromine's all the way back here. Which one's in front, the hydrogen or the bromine? The hydrogen, right? So we draw our hydrogen pointing towards us and our bromine away from us. Okay, what about the rightmost? What about the rightmost carbon? Which one's pointing towards us? The hydrogen. So here's our skeleton as drawn. So pretending like our carbons are flat. What is pointing towards us? What is pointing towards us in this molecule? The hydrogen or the bromine? The hydrogen. So hydrogen gets a wedge and the bromine gets a dash. And just to show you one more equivalent structure, if we rotate it so all of our carbons are drawn flat like so, we can show via rotation there are many ways to draw out this product. So looking on the left first, we see the hydrogens in front and the bromines in the back. On the right-hand side, on this method of drawing this molecule, what is in front? The bromine or the hydrogen? Which one's in front when we draw the molecule in this way? The bromine. Yep, exactly right. Okay, so these are the three main methods that we'll draw out our carbon chains in. And I really want you to start where you keep your bromonium ion flat. Draw it flat and draw your substituents pointing towards and away from you. Attack the bromonium ion, draw your product with the bromines flat, and then rotate. I find students get really confused if they skip a step and they rotate too early. Does that make sense to everyone? Does everyone understand how these three structures are all identical? Does everyone understand how these three structures are just rotation? And I can show that to you. Notice via rotation, we're back to our original structure. And if we do another rotation, other way. We do another rotation, we're back to the original structure that we started with all the way at the beginning of this problem. Does this idea make sense to everyone? How we can draw the same product multiple ways? This is why I recommend you have the model kit and use the model kit for this section. Okay, so that's our first stereochemical outcome that we've analyzed, which is for our Z alkene. Let's now analyze and let's focus on our E alkene now. Okay, so just like always, we're going to draw the first step. And what's our first step? What's our first step? What's the first step in electrophilic dibromination? What's our first step? What's the first intermediate that we make? What do we make first? What's our first step? What's the first step? What's the first thing that we make in electrophilic bromination? What's the first intermediate that we make? What's the first intermediate that we make? Yep, we generate our bromonium intermediate. Exactly right. Okay. So let's draw that out. Perfect. Even the arrows are correct from the student proposal. It's great to see. Okay, so we make our bromonium intermediate. And let's begin to add our dashes and wedges. Let's begin to add our dashes and wedges to this process. So looking at our camera, here is our trans alkene or our E-alkene. Does everyone see how the two carbon substituents are on opposite sides of our alkene? Does everyone see that? Does everyone see how they're trans to each other? Okay, now our bromine, our bromonium ion can either form on the top face or the bottom face. Does it matter which one we choose? Do we get attack from both anyways? Do we get a mixture anyways? Is there any difference between the top and bottom face? Any difference whatsoever? No, there's no difference. You're going to get a mixture. That's why even in this first case, we also get the enantiomer. So you can have the attack from the top or the bottom face. Doesn't matter. Let's arbitrarily choose the attack from the top face. Okay, so we slot that in. This is why I like to use the carbons in your model kit with 5 substitution holes, because it makes it easier to draw this bromonium intermediate and show the attack. But that's just me. Okay, so now that we have this set up, now that we have our bromonium intermediate set up, what do we notice is different? Looking at our stereochemistry, what 2 species are in front? So on the left, what's in front? So on the left, what's in front? What do we have in front? Hydrogen. Okay. Okay. Now, of course, you also get the enantiomer. So don't worry if what you're drawing looks like almost the exact opposite in terms of the arrangement of substituents. So the hydrogen's in the front on the left, the methyl's in the back on the left. And on the right-hand side, what do we have in front? The methyl. So we draw the methyl with a wedge, and we draw the hydrogen with a dash. Okay. Does everyone notice how the bromonium intermediate that we have for the E-alkene is different? Does everyone notice how the bromonium intermediate that we have for the E-alkene is different? Okay, now we can certainly attack at either position. Both positions are equally substituted. So we're just going to arbitrarily attack for consistency at the left carbon. So we're going to arbitrarily attack at the left carbon. What's the only rule for this attack? This attack must occur. Is there any rule? Can I attack from the same face as the bromonium? Can I attack like this? No, it has to be opposite. And the reason for that, just to showcase that, the reason for that, if we think about our sigma bond, opposite to our sigma bond is the sigma star bond. And our bromine is attacking the sigma star. So it's attacking from the opposite side to our carbon-bromine bond. So we're going to attack at the left-hand side, and we're going to break our carbon-bromine bond and open up our bromonium. Okay, Now all we have to do is draw what we see. Now all we have to do is draw what we see. Okay, so I'm going to draw my bromines flat just like before. And now what is in front, pointing towards us on the left? What is pointing towards us? What is pointing towards us? Hydrogen, right? So we're going to draw a hydrogen with a wedge and a carbon, the methyl group, with a dash. Okay, on the left, what is pointing towards us? What is pointing towards us? Carbon. Okay, so we're going to draw the methyl with a wedge and the hydrogen with a dash. Okay. Now, I'd like you just to compare, and this is why I'm zooming out, so you can compare and get the full view. Ooh, what happened there? It decided to zoom out all the way to the next page. Don't worry, I have us covered. Okay, so comparing these two structures, does everyone see, or is the stereochemistry the same or different in these two structures? Is it the same or different? They're diastereomers, and that's critical. That's critical to note. And I want you to draw this in bold ink in your notes. The dibromination products, if you have a different alkene stereochemistry, will be diastereomers or diastereoisomers. They have the opposite configuration at one stereocenter. Does everyone see how only one stereocenter is different? That's why these reactions are known as stereospecific reactions. Whatever stereochemistry you start with for your alkene, you get a different dibromination product based on that stereochemistry. Z gives one product with a defined stereochemistry, and it's an enantiomer. E gives a unique diastereomeric product, and it's an enantiomer. Does that concept make sense to everyone? How whatever stereochemistry you start with directly impacts the stereochemistry of your product. Does that concept make sense? It's called stereospecific because you get a specific stereoisomer and it's an enantiomer out if you start with a given stereochemistry. Okay, we aren't done. We aren't done. I want you to be able to draw these in multiple ways. So we're going to do some rotations. So what I'm going to do now is I'm going to rotate the molecules so my carbons are in the typical zigzag pattern. Okay, so I've rotated the molecule and now I'm just going to draw what I see. Okay, so after some rotation, we found that this structure is equivalent to the following drawing. Now let's do this piece by piece. So my question to you is, looking at this position, is this bromine pointing towards us or away from us on the left? Is this bromine pointing towards or away from us? Towards. Okay, so we'll draw the bromine with a wedge. Okay, what about this hydrogen? The hydrogen then must be pointing away from us. Okay, now let's look at the right. Looking at this hydrogen, is it pointing towards or away from us? This hydrogen on the right, towards us. So we're going to draw a wedge and the bromine gets a dash. Okay, the final way of drawing this structure, all we're going to do is we're going to rotate our carbon-carbon bonds and we're going to draw them like so. And now in this arrangement, where are both of our bromines? Are they pointing towards us or away from us? How are these bromines pointing? Towards or away? What do you see? Compared to the hydrogens, which are hard to see all the way in the back, are these bromines pointing towards us or away from us? Towards, yep. So both the bromines would get a wedge. The reason why I'm showing you this is because you need to be comfortable going from reactant to product and then rotating your product so that it has the correct stereochemical configuration and the skeleton is drawn in the correct manner. So for example, I could give you a problem on the exam where I say match the reactant to the product for the following conditions. And you may have to rotate your molecule to get the product exactly the way that I've drawn it. Does everyone understand how these three structures all come from our E alkene, and they're all the same structure? And of course, you have the enantiomer because you have two faces for attack. Does this idea make sense to everyone? Does this idea make sense of stereospecific reactions? Does this concept make sense to everyone? How does everyone feel about this? Comfortable, uncomfortable, unsure? Just be really careful. The alkene stereochemistry is critical. Okay, so let's test what we've learned. And I'd like you to draw a mechanism for the following reaction. And I'd like you to predict the products of the following reaction. So let's try to draw an arrow pushing mechanism for the following reaction. And I'd like to see the product drawn with stereochemistry indicated, if stereochemistry would be appropriate to indicate. Notice the keyword here, if stereochemistry would be appropriate to indicate. What am I saying there? Well, try drawing out the two possible products. Do you genuinely get a mixture of enantiomers in this case? Often students like to tack on the phrase plus enantiomer and call it a day, but it's important to be rigorous in your assessment such that you make sure that you actually will generate enantiomers. So let's try to predict the products from this reaction, and let's try to draw a mechanism. The mechanism should always be your starting point because that is what directly tells you how you go from reactants to products. It is the mechanism behind how we convert reactants to products. So start from the mechanism and then work your way out. I like the phrasing in the chat looks good, but I would say the bromonium adds at the top face and then bromide attacks from the bottom because the alkene is doing the attacking in the first step because the alkene's the nucleophile in this process. Does that make sense? Okay, so let's try to get some products drawn using the annotate tool and make sure you're specifying stereochemistry. This question is a common type of trick question that is commonly given on the ACS and other exams to check that students are paying attention to enantiomers and diastereomers. So let's try to draw some products and then we'll talk about this example. And really don't be shy to contribute. You can also send me a picture of your proposed mechanism and products, but this is similar to what you'd see on an exam, so you should be comfortable trying to process these examples. And it's really important to not flowchart these too much. Just think about each step, think about what's happening, draw the mechanism step by step, draw the products, and then think about both the products you can make and whether they're the same or different product. And don't be shy to share your proposed mechanism or products using the annotate tool on the class whiteboard. So don't be shy to draw out or share a picture of your proposed product and mechanism, and we'll discuss this example in about 3 to 5 minutes. Does anyone have any questions on this example? I really want to give students the time to work through this example independently and grapple with a question that is pretty common in the homework and pretty common on the exams. Is everyone comfortable using the annotate tool or sharing a picture? If you share a picture, I can also draw that on the class whiteboard. But I really want students to practice drawing the arrow pushing mechanisms, predicting the stereochemistry, just like we did in the earlier examples. So we know this alkene is a Z alkene, just as a hint. So let's try to draw out the mechanism and expected products. Yep, we have coordination of our bromonium. And we're even going to start to see the arrow pushing mechanism for that. That's great to see. That's great to see. Perfect, perfect. So let me redraw that so that way everyone in the class can see, but that was perfect. That's exactly what I'm looking for. So we have the attack, and we have the attack of our alkene on our bromine, and we end up with coordination of our bromonium ion on either the top or bottom face. So we have two options. So option A, we have coordination on the top face. or we can have coordination of our bromonium on the bottom face. Okay, so now that we have our two possibilities, what is our next step? So these two possibilities will potentially give us a pair of enantiomers, but are they really enantiomers? That's at the heart of this question. We have the students saying they're identical. Would you elaborate your point by showing the mechanism to make our two products? So that way we can look at our two products and compare them. It's interesting that you're saying that they're identical. And let's try to collect some more evidence to potentially support that or refute that idea. So what would the next step be? Now that we have both of our bromonium ions, what's our next step? What happens to these bromonium ions? Would anyone like to build off of this? We have our bromonium intermediates. What happens to these bromonium ions? We have bromide floating around. What happens to these bromonium ions? Let's try to keep working through this example. Would anyone like to draw the next step in this mechanism, the attack on the bromonium ions? And let's be really picky about the stereochemistry here. Let's be really picky about our stereochemistry. So just to help everyone visualize what's going on here, just to help everyone visualize what's happening, let's take a look at a model for each of these structures. Let's take a look at a model for each of these structures. So we have a student drawing the attack of the bromonium ion. So currently, we have the following bromonium ion. And as the student noted, the attack occurs on the opposite side to our bromonium ion. So if our bromonium ion is pointing up, then our attack will occur from the opposite face, on the bottom face. Does everyone see how the attack occurs opposite to the bromonium ion? Does everyone see how the attack occurs opposite to our bromonium ion? Can I get some feedback in the chat? Okay, so we're going to attack opposite to our bromonium ion. Both the carbons are equally substituted, and we open up our bromonium ion. Okay, so to redraw this top attack in another way and to help carry the proposed mechanism brought forth by one of your classmates. So we have our bromonium ion and we drew and we have both of our methyl groups, okay? And we drew the attack of bromide on the opposite face to our bromonium ion, opening our bromonium ion. Likewise, so this is the top face attack. So let's draw that out. That in turn gives us the following product. Okay, and now my question to all of you is, which species are pointing above are pointing up. In this ring, so looking at the left-hand side, what is pointing up? What is pointing up towards us? Bromine. Okay, so on the left-hand side, we're going to draw the bromine pointing up. And as a result, mind you, the methyl is pointing down. And on the right-hand side, what species is pointing up? On the right-hand side, what is pointing up? The methyl. So the methyl is pointing up and the bromine's pointing down. That's option A. Okay, let's look at the attack from the bottom face, which would be option B. If we have our bromonium coordinated to the bottom face. One moment, let me make that for you. Okay, so let's suppose we have our bromonium on the bottom face. We can then attack and open up our bromonium ion. So let's suppose arbitrarily that we choose to open it up on, let's suppose that we choose to open it up on the left-hand side. So we kick open. One moment, let me reset OneNote. Give me 1 second. This is a really important point. Allow me 1 moment just to reset OneNote. Sometimes when there are a lot of things, one moment, let me reload OneNote. Okay, we're all set for that. Give it 1 moment. Okay, so continuing on with that idea. Okay, so continuing on with that idea, we are viewing the attack of our bromonium ion. We are viewing the attack of our bromonium ion from the opposite face. So we're attacking from the top face and we're opening up our bromonium ion. So let's show that on camera. So we are attacking our bromonium ion and we're opening it up from the left side. The left and right are equally substituted, so there's no preference. Can everyone see this attack? Can everyone see this attack? Okay, so we attack and open up our bromonium ion. And now all we have to do is draw what we see. Now all we have to do is draw what we see after the attack. Okay, so my question to all of you is, on the left-hand side, what is pointing up? On the left-hand side, what is pointing up? Bromine, okay. So our methyl's pointing down. And on our right-hand side, what is pointing down? Bromine, yeah. So as we notice, in this case, our two possible products are identical. They are not enantiomers. We observe identical products. And even if we had attack at the opposite carbons, and suppose that we happened to generate the following product. These two structures are identical via rotation, and I can prove this to you. So here's our first structure where the bromine on the left is pointing up, the bromine on the right is pointing down. I flip this around. So let me just check to make sure. Let's check to see. So this is another possible product. Let's compare these two products and check to see. Let's check to see if we attacked at our other position. So if we attacked at the opposite carbon, we would generate the following product. And now let's compare these two products and check to see if we end up with enantiomers or if they're identical. Okay. So with that said, this is our first product. And let's see via rotation if we can get this second product. So what does everyone think? If we compare these two products, are these two products identical or are these two products enantiomers? What do we think? Let's take a moment and really compare them. Are these two products identical or are they enantiomers? What do we think? Are these structures non-superimposable mirror images? So, is there any way via rotation now? We see in the chat that some students are proposing that they're identical, other students are proposing that they're enantiomers. Let's do a hard check using stereochemistry. So assigning priority 1, 2, 3. So this center is S. And this center is S. Looking at this structure, this center is R, and this center is R. So what do we notice for our two possible products, for our two different sites of attacks? Are these two products identical or are they enantiomers? Enantiomers. So as we see, depending on the site of attack and depending on the face that our bromonium ion coordinates, we either end up with with identical products or a pair of enantiomers. So in turn, as we can see from this reaction, we would generate a pair of enantiomeric products. That's why you always put plus enantiomer. But it's always important to check to make sure that the enantiomers are genuine enantiomers and that they are not identical. Does that idea make sense to everyone? Does that idea make sense? Does everyone see how to draw the mechanism for this reaction and predict the products? And does everyone notice how different sites of attack lead to different enantiomeric products? Does this make sense to everyone? Perfect. This is a great stopping point for today.